now. All right, so my name is Zach Schwereb-Conti, and I'm a research associate at the Alan Turing Institute in London. I would also like to introduce my colleague and co-organizer who is present today with Ben, Andrea Pizzaferato, and he is a visiting academic at the Alan Turing Institute and at the University of Bath. For those of you who are not familiar with the Alan Turing Institute, this is UK's National Institute for Data Science and AI. I'd also like to say that, on a side note, if you are keen to share your work under this remit, please do come forth and get in touch with us. We'd be happy to find you a suitable slot. As for the format of the seminar, Ben will talk to us for around 45 minutes, followed by a Q&A session. And of course, feel free to ask your questions either in person or via the chat. Now, without further ado, I'd like to introduce Ben, who is our speaker for today. Ben, would you like me to read your bio, or would you like to speak about yourself, your background?
Yeah, I can talk a little.
Fantastic. Okay, then the floor is yours.
Thank you very much, because I forgot that I should introduce myself. But yeah, so my name is Ben. I am working with Guy Schumann at RSS-Hydro, where we do flood modeling and flood detection. My work in particular is on flood detection using optical satellite images. I am by trade a physicist, and I have pivoted towards machine learning quite recently. So this is one of my early ML experiences, and I'm very curious to hear from the people listening what they think, because I will introduce a lot the problem, why it is hard to detect floods correctly, where they differ, and that not all floods are made the same, and a few of the shortcomings of traditional methods, with the goal then afterwards to show our pretty simple machine learning approach, and also get some feedback, maybe things that by intuition or by your background you might want to try if this was your problem. So with that, I will start with a few images from floods, and that they are not all exactly the same. So let's see if I don't need a clicker if I'm this close to the computer. Come on, what's happening now? Okay, a little lag. So here's a very simple and beautiful case, probably the kind of flood people have in mind when they think flooding. We see the main river, and there's a very clearly, like not the way it's supposed to be here on the southern side, a little bit of floods here to the left and right. So this is a very classical example of a riverine flood that could also be solved with classical methods, like there's some where you just have a ratio of a few infrared and visible light signals, and with that you could already do this. But it's not always this easy. Yeah, okay, there's a bit of a lag. Here's another one, which just to show how diverse the manifestation of a flood can be. Depending where you are, what your vegetation is and what sediments you have, it manifests completely differently. So this one is in Madagascar, and it's it's toward the northern part in the national park. And this bright orange manifestation is absolutely crazy to see. There are similar ones around the world with jade coloring and so on, which just shows how diverse it can be, and that it's pretty hard sometimes to find something that generalizes to multiple cases when they are this different. Now to a little bit of a harder one, where it's maybe less clear where the flooding is. This is an example from Pakistan 2022, so from last year. And we clearly see with where the main river is, that there's tons of flooding everywhere, and we have this green jade coloring, which is also part of the flooding. Things get a little bit more ambiguous when we go up to the agricultural fields, where to some extent we as humans, because we try to address it with a supervised method. So it's important that humans are able to do it and to provide labels for us. I mean, the humans is ourselves, so we're not outsourcing it. Yeah, so here are these dark parts where it gets quite ambiguous. And only when exploiting the infrared bands of satellite images can we as humans make a little bit more sense of this. The worst parts are probably like these black rivers that show in black, where sometimes there are little places that are flooded as well, and it's hard to really make sense of it as a human even. This is by far the worst, I believe. Here, still for today, I don't even know what is happening. Initially, I thought here in the north was a lake, but no, there's clearly a river in here. So this, if you try to do labels as a human, it's hell on earth. And so this is in South Sudan. There are a lot of wetlands around here, which is one of the very hard cases that we face. And also one that we definitely haven't solved, just because we don't even have good data to start with. Back to this, an easy one, this one just, yeah. So here you see very clearly, but this one I just showed because of something else that is in the picture. Something that is very common, and that's the clouds. That's the new player that will ruin our fun more often than not, as floods are definitely linked to precipitation. Very often there are days of heavy cloud cover that follow, and which makes optical data pretty much useless in that case. Like this is in Australia, and we see, yeah, something is happening, but trying to reconstruct this is going to be a major challenge. Now, for our project, we focus exclusively on optical data. But still, I'd say that I have to mention another technology that is very good when there's cloud cover. And I will address quickly a few of the limitations it has and why we try to still go with optical data and be a complementary solution for it. So this, I could have written it out. So this technology is synthetic aperture radar, which is an active system where it sends a signal, which is then bounced off the target. And when we talk about Earth observation, like Earth's surface, there is a correlation between the roughness of the surface and how strong the return signal is. So luckily, water, no matter where you are, is pretty much flat, which allows it to be seen as a lack of signal, as a weak return. Like here you can see the river, for example, and a little lake here in the south. And the beauty of the approach is that it penetrates clouds. So here's an example of the same area when it is actually flooded, and it's especially this southern part that has been hit hard. And this is one pretty popular approach that is being used when it comes to flood detection. But it has two limitations, which are due to the fact that it is an active instrument. And this is when it has double bounces or when it is being scattered in some kind of vegetation. So SAR is known to perform without tons of additional research and corrections pretty poorly when we talk about heavy vegetation or urban areas. Another problem is also when there's very steep slopes, which can also lead to some double bouncing or shadowing effect. So I just wanted to address SAR because it's, if there are any SAR people in the room, it's like the obvious thing to go for. And also I'm showing here pretty simple processed images, but the SAR signal is quite complex. There's the amplitude, there's the phase, you can use two things and do interferometry. There's tons of things that are possible with SAR, but with the established method like the hazard algorithm from LIST, for example, that we are aware of and that we have used in the past, these are some limitations that motivated us to go back to the optical data. So in the end, for this project, we focused on open data for Sentinel-2 specifically, which is at 10-meter resolution and has a 5-day revisit time. Its instruments have some bands in the visible light and multiple ones in the infrared, which is also interesting when you talk about water, because the response from infrared is quite significantly different than the rest. So it helps a lot with both labeling and also supporting the machine learning algorithm itself. Now, when it comes to revisit time, if the goal is to detect the flood as quickly as possible after it has happened, there are many other constellations with similar instruments on board, like the US Landsat series. So that's when we talk about actually deploying it and making it useful. And here, the things we have in mind is mostly the humanitarian sector, where the on-ground observations are far more sparse. And often one of the only information available to them quickly is what we have from satellites. That's one of the motivations why to do it. Another side for the more the scientific community is that optical data has been recorded since the 70s, and there's a long historic archive that can be exploited if we ever want to check the flood extents in the same region of known floods and do some analysis about that, which is not the case for SAR, as those sensors are much more recent. But just to reiterate, the main problem is cloud cover. But in any case, now we can come a little bit to what we actually did to solve the problem. So first we have preparing the data, and I'm just at a very high level will show some of the steps we did without tons of details. But one thing we have to do is to reproject the data so it's ready to be used. If there are multiple bands and later on we introduce other data besides the Sentinel images itself, we need to combine them into a single raster. And finally, because these images are quite big, they are like over 100 by 100 kilometers, they are far too large for the GPU to handle. We have to tile it down into small patches that are actually able to be processed for both the training and when we run inference. So we go with this 244 by 244 pixels, which seem to be a size that works quite well. For the machine learning part, it's quite simple what we did. So as it is image data, similar to it, it's not 3 bands, it's more bands, but it's an image data. We went with convolutional networks. So the first one is not one, but we have many different bands. And one of the problems is that we wanted to know if we confuse it or if we just add new bands, if it even helps. Like, is it useful to have multiple infrared bands that are similar to each other in wavelength? So there's this squeeze and excitation network where we do some global pooling and a few fully connected layers, and it will give us the importance of the different channels. This is being multiplied back in to improve performance. So the channel with the highest importance will have the highest weight. And additionally, we can set hooks to extract this information and do some future analysis about what is the most important channel and which ones are redundant and so on. Then we come to the beating heart, and I think most people have probably seen it, the UNet. So it's an image-to-image transformation network. As an input, we have all the different bands, Sentinel image and auxiliary data, which I'll come to later on. And as an output, what we want to have is for each pixel, we have a floating number between 0 and 1, which indicates whether it's water or no water. So it's a single class problem. 1 being water, 0 being no water in this place. So here's a little bit how everything then comes together. We have our raw image, we have our auxiliary data, which can be digital elevation model, and I will motivate that in a few minutes. We have the pre-processing, the stacking, the tiling, and that goes through our machine learning algorithm. On the other side, of course, we need some labels. Here we have the ones that are prepared by our experts and are again being pre-processed, reprojected. This also has to fit, of course, then being tiled. We compute the loss, and it's a very classic supervised task that we try to solve. And then when we run inference, it's pretty much the same, just that we do not have, of course, the labels. We just apply our machine learning model. We have all the different tiles that we then have to merge back together. So there are a few steps to recover the projection at the geotransform, which gives us then one image, which is the prediction, which can then be used by our potential customers. All right. So let's show a little bit what this looks like with a very basic case. So the first ones that I want to address is the cloud-free case. So we don't have to deal with the clouds just yet. And what we do is we do a random split. When we have our area of interest, we will end up with a few thousand tiles typically. With one case that I will show near Balaton, we have in the 4,500 tiles available, and we just randomly split them. As we have no overlap between the tiles, this shouldn't lead to the problem that we train on the same data that we validate on. because of course that's absolutely to be avoided. So it's no overlap between the tiles, and that's the reason why we use it like that. I will show some details about this, but here's the Balaton case and the Sudan case from before, where we applied this very simple method. And as a metric, we use intersection over union. Should I explain intersection over union? Or I think I just will.
Thank you.
Sorry?
Please go ahead.
Okay, yeah. Because I never know like who exactly in the audience is, but so intersection over union is a metric where you consider the area of your labels and the area that you predict. And when both intersect, that's a positive. So if everything intersects, you will have one on top of the denominator. And when you have the union, oh God, I'm not explaining this right. I should have done a little picture. But yeah, high intersection is good. And if the union is bigger than your intersection, that's bad. So you just do the intersection over union, a simple ratio. 100% means the intersection and union are identical. And the lower it goes, the more you have either false positives or false negatives in the mix. In the case that we have here shown on the right, we have Lake Balaton, where we just ran it on permanent waters because it was very simple to create those labels. We could exploit, in this case, the OpenStreetMap labels and just correct them manually because there are a few problems in the Balaton, in the Danube River. And with that, we reached the 93.6%, which we are very happy with, and which also showed us that the simple architecture can indeed address the problem and do the segmentation task. The second one, Sudan, that's an actual flood. And in this case, the 88.9% also shows that it is possible. And in this case, if you remember, there was already a little bit more color differences that were visible between the flooded area and the other area. And it just missed a few parts, like here in the south, there's like a little body of water. Oh, my mouse is not that fast. Yeah, like there are a few things that were missed that are very similar to the ground. But in general, it takes the main areas and finds them. Here are a few close-ups. So the colors that you see is in red is the labels that we have. And in blue is what our inferred detection is. And so whenever you see red, that's a false negative. That should have been caught by the algorithm. And this here is now the Danube, quite big river, and the out ones in general work. It does have some limitations where it gets smaller. And especially for small streams, we see that when it gets to the size of 1 or 2 pixels in width, it really stops working and it completely misses them. But the big outruns are, the big rivers and the outruns are definitely being caught correctly. So are lakes, as long as they are not too small. Here's another example near an urban area where we see the same problem with small streams and with some of the water reservoirs near agricultural land. And in this one, we saw that sometimes the water has white reflectance, very bright. Maybe it's a bit of perturbed water, we're not exactly sure. But those are failing quite badly. Like this whole area, which is quite big, had a similar reflectance to what we see here on the border and was completely missed. On the false positive side, there is very little. It's mostly false negatives that we see. So let's go to something maybe a little bit more complicated or interesting. Or maybe, should we open a few questions now if there are some?
Yes, if there are any questions, if you're happy to.
Or comments, both.
So for your bands, you have exactly the same resolution for your visibility or infrared?
Yes, those are the same resolution. There are a few extra bands available at 20 and 60 meter resolution. And we also tried introducing some of them, but then we have to, of course, resample and get everything to 10 meter and do some interpolation in that case. But the ones that I showed there, there is band 8 that is at 10 meter, but there's a few others that exist as well. But they are a bit redundant, they aren't that helpful in the end.
When you were talking about SAR with those, you referred to them as challenges in terms of the double bounce and the vegetation. Were you looking at what wavelengths of SAR were you considering when you were thinking about that, firstly? And secondly, have you considered perhaps you might be able to exploit those aspects that you consider to be problematic? They might actually help you to differentiate between flooded areas and non-flooded areas when you look at different polarization.
This is a very active field of research, and there's definitely, for sure, more that can be exploited from the SAR signal. That's not what I myself am able to do or aim to do within this project, but I know it's a very active field of study. So I think there might be in the future ways that work better and address these limitations or even exploit them to be a strength, not a weakness. But I myself don't know that much about it. But Guy is on the line. He might know a little bit about it, if he wants to jump in about SAR.
Yeah, I mean, the question was always like, you said you said it at the beginning, the complementarity of the optical to the SAR. So SAR has its limitations, but of course, exploiting the SAR signal. Did you mean the question, was it more related to how we could use the SAR signal within this machine learning for the optical, or was it in general the SAR signal? Sorry, I didn't.
Just in general, I know obviously if cloud covers the biggest problem, then SAR's obvious.
Actually, it was a suggestion of ESA also to try and include SAR at the very beginning, but then the trouble is, one of the difficulties with SAR is that it's, like Ben highlighted a few, it's vegetation. So SAR is not without limitations. Of course, it penetrates clouds and light rain, but of course, if you have things like wind, it can, like high wind, it can be very bad, the signal return. Also, if you have like onsets of flooding, so moving from high soil moisture content to just surface water inundation at the very beginning, you have difference in signal response. So this gets a bit weird in what you see in the backscatter, but then the vegetation, urban areas, etc. And the other very much shortcoming of SAR is the satellite missions are not that many yet. But what I mean yet is that SAR is typically used in flood mapping to have a comparison between a dry image and a wet image. That's the easiest in the SAR processing mode. But if you take, for example, the Sentinel-1 mission of SAR, yes, it's been great. 2 satellites were up there, then suddenly there was only 1. I shouldn't be laughing, but ESA lost one of the satellites on SAR. So this created a whole lot of difficulties in the community when mapping floods because of this constant need to look for a dry image, which is the easiest approach. And then also the optical ones are in history. If you go back 50 years with Landsat. So I guess if what Ben shows here is applied to Sentinel-2, we could essentially apply it to also Landsat and longer archive missions. And then the commercial world is more moving towards optical, although SAR is picking up very, very quickly. So I guess my answer is that most SAR satellite missions are opportunistic, so they're not constantly switched on. There's a lot of data that's gathered, and SAR data is a higher bit rate, so there's much more data. So very often there are a lot of places around the world where SAR is not having great revisits, and with all these limitations. But then you're right, the cloud cover is the biggest advantage when you look at SAR. I don't know if this answers your question, but SAR is actually most used for flood mapping more than optical right now. But I think there's going to be a shift, like Cloud to Street, for example, another company quite well known in flood mapping from remote sensing. They started with optical, now they complement it with SAR as well, but they started with optical for the similar reason than we just did. But their whole company is based on EO flood mapping. So yeah, I think I'm not sure if that answers your question now.
I think, yeah, okay, I think it's good. Anything else?
We have one question from Marcus.
Mm-hmm.
Marcus, go ahead.
Apologies if it's loud. Yeah, first of all, thanks so much for the talk so far. It's really interesting to see like different kinds of problems and that were I had a question originally on whether the resolution is an issue, and you answered that just recently. I don't know if do you know if anybody's ever looked into subpixel methods for these sorts of things? And I don't know whether that's tough because of the relatively low temporal resolution.
It was a bit choppy, the quality, but you asked about subpixel.
Yes.
So we didn't do it in here. I don't really know how to approach it. What would be the best there? Because here, the way we set it up, the problem, we keep it quite simple. We have a single snapshot in time where we want to have an algorithm run over it. We don't really consider what the area looks like before. There's no time series or anything, which are all ways to maybe in the future go. So I don't know exactly how. I mean, I didn't really think about it that much. But if you have a method in mind, I would love to hear and look into it, because that's also one thing that I hope to get out of the talk, like inputs from the community.
Yeah, I mean, I've not spent too much time on subpixel stuff myself, but I do know that there's quite a strong requirement of like a good temporal resolution. But then I wonder if, like, again, I wonder if to do with using different wavelengths, you can sort of get over that problem in the fact that you've got like a 5-day cycle, but then you can sort of exploit using different wavelengths to sort of extrapolate. I don't know, but I don't really know how the science works exactly, but yeah.
All right. Yeah. Well, it's something that we can look into. I mean, it does sound like a promising approach to go. So there was, yeah.
We have another question from Stephen, who asks, are you considering each image in isolation, or are you comparing images to an image of a previous state or even sequence of images? I had a similar question to actually.
Yeah, so this is really, we always take the image in isolation. We try to just use the signal that is available for that one moment in time and try to get the best possible segmentation out of it.
Are you, if I can add on to that, are you looking into more of a dynamic approach, so trying to capture the dynamic behavior of a flood rather than one snapshot in time? Or do you have any intention?
It's an idea. It's definitely an idea that has crossed our minds, and it always depends on now how much resources we have to keep developing. But it's definitely one, especially if we do like a more proper time series analysis and have a bit more information about, like, you know, with SAR, there's the using the dry image, and then the case of the flood, and this difference is what is being exploited. And I believe something similar could happen here. Now, I think one challenge that will happen is that the cloud cover will be vastly different every single time. And it's something that we need to think about much more if we want to go into time series, with the exception if we have floods in the desert, pretty much like the Niger River, where the clouds usually dissipate quite quickly, or this year's Pakistan flood, where also there were a lot of images available, both dry and wet, of the same area. I think there, this approach could yield, could really push performance a bit further. So yeah, it depends. If we have the resources to push the project further, it's something to definitely look into, especially for the cloud-free case.
I mean, this is key. If I can quickly add, it's interesting because this thing is exploited in the MODIS series of satellites by NASA, since they have a daily coverage, but a very coarse resolution. So they use this multi-temporal dynamic to actually mask out the clouds quite effectively. So they have an 8-day average product for floods, but they have a very coarse resolution. And so the issue is also that we having Sentinel-2, it is not coming back frequent enough. And it's never on exactly the same area. So if we look at something like Planet, sub-daily coverage, maybe that gets very interesting. But there, again, the quality of images are quite different to Sentinel. You know, Sentinel and MODIS and these missions are scientific missions, whereas Planet's data is commercial. So the quality of in the image, the spectral quality differs quite significantly from image to image. So again, even if you have sub-daily, but there you have the challenge of the spectral quality. But I think machine learning could handle some of that. It's very interesting, actually. I was always thinking in the back of my mind to talk to Planet about this approach. You know, what could we do if we had sub-daily repeat of a flood? But then Ben is right about the cloud cover, so we have to be very careful because we got very high dynamics on cloud movements. Thanks.
Interesting. Thank you so much. Right, Ben, I think you can.
Yes, exactly. I'll go on, and I think I'll make it to the end, and then we can do a second round. Okay, so now when we talk about how to deal with clouds, we have two problems here. One is the inputs, because when you consider the area that is clouded, from Sentinel, you get pretty much no information about what is happening here. So you are inherently stuck with that. And the second one is labels, which I come back to. So one thing that we tried, and this is fun experimental, like in a real flood case, I think it won't work. But what we have is that there's a product out there, the digital elevation model, which gives you for every pixel the elevation at that position. And this one is available everywhere. So it also extends below the clouds. And as water flows downhill and most flood-prone areas are low-lying and flat, it's something that we just try to introduce into the model and see how it uses it and how it deals with it. Now, one additional, this is the auxiliary data I talked about before. One other type of auxiliary data added, that we added is the flow accumulation. This is if you consider a rain event, you have always a whole catchment basin where all the rain is being caught and it runs down into some exit point, like it runs into the river and then out of your area of interest. And within the catchment basins, you can compute the flow direction, where the water is going, and count up how many of these cells run into each other. So if we consider the 20 here, that is by checking how many of them flow into it. So you count all the neighbors and the neighbors of that point into it. What this gives you is information about how this individual pixel is being situated within the whole catchment basin. So that's the second quantity that we give our machine learning model to see what it can do. For the labels, there is the problem that if you don't see the flood, you can definitely not, as a human, go in and try to label it. There's no way. You are completely lost. So there are a few ways that you could do. You could use SAR, but then we inherit the limitations that we addressed before. Another way is to label cloud-free examples and synthetically add clouds afterwards. This is one that is, I believe, quite promising. And recently there has been a Python library published that does this with for RGB images. So we could extend it to the bands that we have, but it would require quite a bit of effort to know how this looks correctly in infrared bands, for example. And then there's the last one, and in the end, we just wanted to try a first very simple case to see how the idea of adding auxiliary data works, and this is using permanent waters. Whether there are clouds or not, the permanent waters remain the same, so we can exploit them as labels and just see if the algorithm manages to do anything. So this is the case that we consider on the left. It's just showing a little bit bigger. So it's Lake Balaton, very clouded on the left, patchy cloudiness in the east. And I will just show a little bit what it looks like. So that's just the image itself. Here are the labels as we take them from OSM, just like before from OpenStreetMap. And I will zoom into some because it's a bit low resolution what I chose here. I'm sorry about that. And here's what we actually inferred. So first off, there's like this surprising behavior that even in fully clouded areas, the algorithm does something. And when we take a closer look, it's just a bit of lag. we see that outside of the clouds, it does a pretty good job. When we go in, it loses a little bit of its confidence, but it is not really interrupted. And at least the Danube, it is getting without interruption. And in the small streams, it starts being a little bit more shaky. I have a second, even bit more extreme example where it, sorry for the lag. And there it is. Where it penetrates deep into the cloud cover and only fails once the streams get smaller. So we saw these results, and we were definitely thinking that it doesn't really make sense that it works, because I mean, at least there's no information in these, if we consider an entire that is completely clouded, there's no information from the Sentinel image that is being able to be exploited. So it has to rely exclusively on the DEM, which is exactly what it does. What it actually does is it figured out that there's a very heavy correlation between very flat slopes and the flooded areas. But this, of course, has a very fundamental problem, that the auxiliary data, the DEM that we use, the digital elevation model, is time invariant. At any moment in time, it's the same product. It is being updated very rarely, and it doesn't matter if you use it during a dry season in summer or if it's during a 100-year event of flood. So you have the same input data that is not dependent on whether there's a flood or not, and so it will always give this result. So it will manage to find permanent waters, but that's not our goal. By extension, it might even be able to find flood-prone areas, but it will definitely not be able, just like that, to find the actual floods under clouds, which was also not really to be expected. But so what is needed to make that happen is some kind of dynamic input that is actually dependent on the moment in time that we consider, which can be rainfall. So this whole clouded case is more of a scientific curiosity. Like we saw it, we liked it, we played around with it a little bit. We don't see it necessarily as viable, because these are definitely the cases where SAR should be used. So from here on, we focus more on the cloud-free cases, but it's something that I wanted to share because for us, this was a cool moment to see what with a simple supervised learning task, it managed to still segment, even though the case looked quite desperate before we started. Here, again, the intersection of a union, that there is a drop of about 5% in performance. But yeah, so the main thing, it's not viable for commercialization, but I think it's interesting to think about this problem and how we can improve it. I have 15 more minutes. Okay, so I will be a bit quick. So the last thing that we were thinking about is how well it transfers. So far, we have always relied on the random split. We take one area, we tile it, and then we do a random split on what goes into training set, what goes into validation set. As such, it doesn't matter if it's random, but we take it from the exact same distribution. And we didn't really consider yet how well it transfers if you train a model, let's say in Germany, and then you want to apply it in the Netherlands or something like that. So here in this second part, we considered the Pakistan 2022 flood event, where there are a lot of cloud-free images available. And we chose 2 of them, and we labeled them to try to find out how well it transfers if we are not doing the random split, but training on one and applying to the other. So we have already quite a few differences between those 2 areas. This one has a mountain range in the west, which is not really present in the Pakistan South image. This geological structure right here is pretty low lying. That's not a high mountain. It's something that is only a few hundred meters tall, whereas this goes up to the thousands. This one has far more agricultural lands. So there's in general a lot of differences between these 2 areas. Now, when we try to train on Pakistan Center and apply on Pakistan South or vice versa, we get pretty miserable results. We are in the 34%, 55%. These are results that are not useful at all. Lastly, we also just did the random split on Pakistan South to see if there's something inherently harder with the task. But again, we reached the 93% mark, which shows that it is similarly hard as a task than, for example, Balaton, that it is feasible. So with the right data set, we should be able to improve this. And we had a few other data sets available to us from Sudan, as we showed before, or from Spain. So these two we had ready, we had labeled, and we just threw them into the training data to see how well it performs. If even though Sudan is completely different vegetation, completely different topography, it's very flat, and Spain is much more temperate, but contains some hills, a little bit like the Pakistan case, the Pakistan center case. So we tried this and to see if we can get any increase in performance, and indeed it is. We got like quite substantial increase, even though the features between Pakistan North, Spain, and Sudan are so different from South. Just having a little bit more of a diverse data set seems to help a lot. So, yeah, so now, oops, sorry. So just taking a look at what it, like 83 is much lower than any others that we have shown now. So transferability is definitely not trivial. And I will show a little image and zoom on one or two places. Okay, so this is not helping. I will zoom to show you a little bit. But if you remember, there was the main flood in the center from the northeast to the southwest, which it recovered quite well. And then in the agricultural land in the north, it's a little bit mixed, but near the streams and the rivers in the south, it fails quite miserably. And overall, there are a lot of false negatives that we see here. When we zoom in, we have on top the model that we're interested in. That's the one that has the 83% intersection over union. And here near the urban area with the main flood, it does miss some patches, but it performs okay-ish. Like also here, this canal that goes through the city, we missed it in some parts. But when we go to these black-looking rivers or small streams, it fails quite miserably in general. I see 10 minutes left. On the bottom is just the one where we take Pakistan South with the random split and we train it on itself to show that it's absolutely feasible to get a model out, but the transferability itself is really the problem. I'm at conclusion, so 10 minutes is pretty nice there. So one is clearly transferability is hard. We need tons of labels to really make it work. But if we consider a smaller area, a smaller region that somebody's interested in with a specific climate and topography, we can focus on that and get specialized models that are pretty good, like around major urban centers that, for example, an insurance would be interested in. Clouds, in my opinion, are mostly an unsurmountable problem. It is interesting to see, like for the pure curiosity of it, what we achieved with the very basic supervised learning, where a digital elevation model was used to guide our machine learning algorithm. But in the end, I think the cloud problem should be left to SAR, and that this approach that we have studied here should really be a complement. This is something I didn't really show in detail, but adding a digital elevation model also in the cloud-free case gives a little bit of a performance boost. It's not very significant, but it does help. And in the end, yeah, if you're interested in the pre-processing and inference scripts, they are actually on GitHub, and you can use it. There's a little bit of documentation missing, so I think it's best if you just reach out to me, because I will still need to, at least for the models that we made available, to say what it is, where it's meant to be used. Because with the transferability issue, if you use it on a random place on Earth, chances are that you get no meaningful result out at all. So with that, I'm at the end, and I should have added key here as well. So we can have...
Yes,
thanks.
Thank you very much, David. Not David, I meant Ben. I'm sorry. So thanks a lot, Ben, for sharing your work. And we do have time for questions. if there are any other questions. In the meantime, I do have one question with regards. So I believe earlier Guy mentioned that you guys also work with physics-based models for flooding. I was wondering if there was any intention to leverage those models to improve things like to bypass things like cloud coverage and so on. And by that I mean incorporating those physics-based representations in the machine learning framework.
So I don't know who's best to respond to this one.
It's I can take it, and then Ben, I'm sure you can add some stuff. But it's a very good question, especially like you said, because in the company we do, and we have a few people, including myself, track record on flood modeling. So it is absolutely true. And in flood modeling, the same drivers as here on the flood mapping for clouded cases Ben showed, the DM is the main driver. So topography is usually the main driver. And although it is quite nice to try and use these physical-based models to see what the ML does with them, but I'm afraid, but I don't know, maybe Ben, I'm wrong here and you can add more, but I'm afraid the machine learning will end up only focusing on the model result, because the model always gives a full extent of a flood. Whether accurate or not, it always gives a nice full extent of a flood without clouds and anything else, and it's quite matching a flat topography, low slope. So I'm afraid that what we see for permanent waters in the clouded cases, we're going to see for most flood events that the algorithm will learn, it will just probably discard most of Sentinel-2 images and then just run with the model-based flooding. But I may be wrong. It is definitely worth a try, and we can, for some cases, try that. So we have some models in some cases, for example, the Niger, where we can try and see what happens. Very curious, because that question has been put to us a number of times. So you're not the first one to ask that question. Actually, Isa, the technical officer himself, Bertrand Lesseau, asked exactly that question as well at the very beginning of the project. He said, well, couldn't you use, instead of just topographic wetness index, couldn't you use a physics-based model, dynamic, for that? And my answer was pretty much the same. And since ESA is an Earth observation-based institution, it's also okay to not use like model predictions, but it's still an interesting, very interesting question, I think. Yeah.
Because I'm thinking about this. Oh, sorry. When we have these physical models, they mostly address like we have like the risk for different zones. If that's like an input that can just be given to the model, but it might latch onto it too much. But also not exactly sure how that input looks, because as far as I remember, we always have a scenario that we consider and see what the extent is. I don't know if there's like a way of creating an input that gradually says like how much at risk with some arbitrary unit, I don't know, the different areas are, and that could be an input, which then kind of functions like the DEM, but more explicit, because DEM implicitly has some of this information. Yeah, I think we can go down a rabbit hole here, but maybe it's good to questions.
Well, thanks for your replies. So we have a question. We have a raised hand from Marcus again, and then I'll head on to another question from Emily. Marcus, go ahead.
Hopefully you can hear me better now. I think I might have hopefully fixed the problem. Yeah, just to link on to what the last bit of discussion was, like the way that I normally see like physics embedded machine learning problems is you've got two main branches, either model solution discovery or model discovery. So like model solution discovery, it's a lot more free reign. You might be guiding it with a little bit of physics, but it's still more towards like a data-driven problem. And then model discovery is you have a model, but you're not, like the most boiled down version of it is you have a model, but you're not quite sure what the parameters are. So the machine learning learns those parameters. And then what we're seeing more and more of is sort of a combination of both, which is essentially that could be, in my brain anyway, is you envisage that like you have a model, it has some physics that you know, but there's more physics that you don't quite know, So yeah, like layer these two different ways of looking at it on top of each other, and that gives you like the benefits of both, with also the drawbacks of both. But then that's another philosophical discussion as well. I don't know whether like these, whether either of those methods, because it sounds like maybe at the minute it's more on the model solution discovery side, and that sort of leads on to the most key question I had, which is like, what were the features that you were using? Was it just optical data, or did you have like topological data, soil data, things like that?
For our input, it's really, I mean, we focus on the detection, so that would be solution discovery, I guess. And the inputs are really just the Sentinel data, and then the digital elevation model, and some other auxiliary data that is all directly derived from the digital elevation model. So there's no physics that we explicitly encode anywhere. And also the inputs are not like derived from solving the shallow water equations or something like that. I was thinking a little bit about this idea of getting a little bit more physics into it, but I didn't really find an obvious way, because there are the shallow water equations, but the problem is our output, for example, gives just the extent. You don't know the depth of it. So I don't think that there's, like, for example, something we can do by modifying the loss function easily. There might be ways of doing it, but it would probably require some intermediate steps to, from extent, extract depth. Then we could use that, for example, to have a loss. Oh, we have 1 minute, sorry. But that was a thought I had in the past, but we never went deeply into it.
Thank you. So we have we have two questions. So one from Emily: which part in the ML model incorporates the physical properties of flood geographical data?
So at the input, we have the digital elevation model, which gives you pretty much topography, where the high-lying areas and the low-lying areas are. This is something that indirectly, but it has a very clear influence on how the water flows, and that is what is like the physics part in quotes.
Okay, we have another question from James. So that's: how do you select which Sentinel bands to use as your input?
Initially we had just one single band by accident, which worked okay, and then we extended it and saw that it isn't that much of a boost. What we found out, which seems to be the case, if we have one visible band and one infrared band, that's the most valuable, because then there's not much redundant information. But if you throw everything in there, it still works and it doesn't hurt. So that's also something.
Perfect. I hope your answer has been questioned, James. Okay, we're right at 2 o'clock, and that's just about perfect. I'd like to say thank you to everyone for joining us today. Thank you, Ben, for sharing your work, and thanks, Guy, for also interventing. We encourage everyone to join us in 2 weeks' time for our next talk. But in the meantime, Happy New Year, and have a great day.
Thank you very much. Happy New Year as well.
Yeah, same for me. Thanks for inviting us. Thank you.
Oh, it's a pleasure. Bye, guys.
Bye. Bye-bye.
Where should I wait at? Oh, there it is.